Yes. So AI review. Yes. These are the subtopics. So brought to you by MLDA, Machine Learning and Data Analytics. So we will be going through the four main concepts that is very important. First is the overview of agents and environment. Secondly is the search, the various type of search. The third one is constraint satisfaction and game playing. And the fourth one is reinforcement learning. So during this slide, and we will also be sharing the slide at the very end of the session. So don't just, turn off and go off. But I believe that the content as I go through, you can also have questions and we will be more productive interacting when the event is happening, right? So do raise your questions because this is how you learn. And in the slide, you can see that there are red and green points. So those are the red ones are like core idea for the quiz. I just came here for A plus. Sure, you can focus on the red part. But I also want to give you the green part as well, because I think these are the part that will help you in the future if you choose to understand the field or go deep into the field more. So over here, it is just a visualization of like the big field of machine learning and AI. Not every AI is very high intelligence on the right. So this is from Stanford AI. If you're interested, you can go and take a look. Right, okay, so let's start straight away. Agent and environment. So what is the key idea here? The key idea are the six big classification of the environment and the agent. So first, you ask yourself, do I have the knowledge of the environment? Does the agent has the knowledge of the environment? Accessible is full knowledge, inaccessible is partial knowledge. Are there the consequences of my action? Will it always be the same, or will it be like probabilistic? It follows a probability distribution. So how does it, what does it mean? Like what is deterministic and like having a distribution? So one example that I brought up here is the idea, if you play games, you have this idea of a critical hit, right? So sometimes when you hit an opponent, some percent of the time, you will have a critical hit, you have double the damage. But when does that happen? You don't know. It's like randomly generated at the back end server, and somehow like if it's like it hits like 20%, okay, now I give you a critical hit. So yeah, it's a League of Legends reference. It is a bad example though, because this person maxed out the critical hit, so every hit is critical. But the idea is the same. I do some action, I expecting some outcome, but the outcome might not turn out as I want. So that is deterministic and non-deterministic. The third one is it episodic or is sequential? So episodic means by episode, every new episode is a fresh blank slate. So how do we classify the episode? So in this context, we classify the episode as one thinking loop. So the agent interact with the world, it forms a decision. That is one episode. So the idea is, does my action now affect the action in the future? Then if it does, then it is sequential. The environment, is it static or dynamic? How to understand this idea? So the agent itself can interact with the world, but the world itself can also change in ways that the agent does not have control over, right? So let's say the mismatch of like static or dynamic comes from like the mismatch of the rate of changing or like the environment itself. So if the agent is observing the environment and taking action at 10 hertz, so it is taking like 10 action per second, and the environment is like changing twice as the speed, meaning that in between the action, while the agent is thinking, the environment is changing. So that is the dynamic environment. The dynamic not only means that the environment changed regardless of the agent action, but it can also change because it is just faster. Like the way it changes is faster than the agent rate of thinking and making decision, right? And the last one is discrete or continuous. So this just define whether the state or the action of the agent is it is discrete, like going left, going right, or is it continuous, going left from any values from 1 to 2, right? You can have the float, right? You can have the decimal number in between. So that is the simple explanation for these. So let's run through. So I believe that annotate. Let's highlight. Yeah, highlight. So I believe that the best way to learn these things is just to run through them all, right? These are the various examples. And I also give the reminder of the 6 different classification category. So slot machine, is very simple. It is quite inaccessible in a way that you don't know what is the number behind, right? Deterministic or non-deterministic? Definitely, I think there is some non-determinism at the back end, right? Because it depends on how the people code this thing. So sometimes you turn the lever. Yeah, exactly. The lever is just one action. Do I turn it? Is it on or off, 0 or 1? If I turn it, what is the state? I don't know. It running at the back end. Episodic or sequential? This is episodic because one turn will not affect the next one. Like I make one decision, then for the next decision, there is no, it doesn't really affect. Yeah, static or dynamic? This is static because my action doesn't really affect the I'm sorry, the slot machine will not change if I don't interact with that. So it is static. And discrete or continuous? So you might think, okay, so the slot is like in circle, right? So circle is quite smooth, so it may be continuous. But you can see that what is important is only the various character, the various symbols. So if there are 10 symbols, then it is discrete and it only have 10 values per wheels, right? So it is discretized. So apply that for chess. Similarly, here, in the chess case, you have full picture of your opponent and of yourself. Fully accessible. Deterministic because I want the pawn to go up, to go straight 1 unit. It will go straight 1 unit. No one can knock it out. Yeah. So here we see that it is sequential because my decision to like move the pawn will block the next move from some opponent. So it is sequential. One decision will affect the future decision, right? And then there are various game. Maybe I will not like go through them all, but highlight the main idea, right? The big category that they might fall under, which is, so you can see StarCraft, right? StarCraft is a game where you have this black area, like fog of war. So the idea is, this is an inaccessible environment. You don't know what the opponent is doing. You don't know the environment if you have not explored. So that is, inaccessible. Monopoly. Okay, Monopoly is another good example of the idea of non-deterministic, right? How do you play Monopoly? You roll the die. You roll the dice, and if it rolls 6, you go 6 steps. So this is where the non-determinism go in. You take an action. What is the action? The action is to roll the die, but the value of the die is dependent on the die. You cannot control that. So non-determinism. But the monopoly itself is, the state is quite discrete, right? Because it is put into different boxes and slots. So in a sense, there is a certain discrete component there. But you can also ask, okay, yes, the boxes are discrete, but the money that we're giving out is quite continuous, right? Like you can go from $1 to okay. Yes. Yeah. So the monopoly, right? So the board game is discrete, but you might ask, but the money is not. So now I would introduce you to that idea. In an environment, there can be discrete and continuous component, right? So this classification is helpful for you to start analyzing the environment and the agent. but some component can exist both variable, both discrete or continuous. Yeah, and yeah. So I think the big picture is yeah, the big picture of this part is just this 6 classification, and I think it can be quite straightforward. So now it is the interesting part. Okay, why the environment and agent is highlighted in green. So it is not included, it's not needed, but I will share with you anyway. So why do we separate the agent and the environment, right? Why can we solve the problem as, let's say, one file, one single Python file, and solve everything inside there? The idea is we want to separate them out so that there is an agent logic and an environment logic. Different people can focus on different things. So let's say if you're doing research in simulation, then you will handle the environment. I will build the best simulator in this environment. Then someone other in some research lab, they want to define the AI, improve better AI. Then they will just focus on the agent. So the idea of separating agent and environment is to compartmentalize. And this code here is from OpenAI. There is a library called Gym, and as you can see over here, the environment is just one single line. I import an existing environment, and then down here, user defined policy. Then here is where I will, program my agent. So there is a separation, just for fun. Yeah. Why the different classification? It helps in the programming of the agent. So as you can see just now, if it's a discrete action, I should put it in an array, right? If it's a continuous action, it is like a floating number. Agent environment definition, probably not needed, so I will move on. But I think this is the idea. I think this will influence the reinforcement learning understanding later. So the idea of a policy, the policy defines the behavior of an agent. So when you say if agent 1 and agent 2 are different, they have different policy, they have different behavior. And usually when you want to solve a problem in, let's say, AI, you want to define a cost function and you want to optimize, you want to maximize or minimize this cost function. If the cost is a good cost, then you want to maximize. If it is a bad cost, then you want to minimize. All right, let's move on. Search, right? So search, in this sense, it is kind of like an optimization method. So just now we go over the big picture of how to define agent and environment. Now we are tackling the various ways we can solve that environment. So the two big search, the search, right? The basic component, I would say, of search is this idea of depth first search and breadth first search. And I think this GIF is quite illustrative of the whole action of what it does. So depth first search is the idea that if you visit a node, you want to continue visiting down the branch. And breadth first search, so you start from 1, you want to explore all the nearby node before you go down further, right? And here we see that it is a blind search. What does it mean to have a blind search? A blind search is because we know the goal when we reach the goal, and we are starting from a source, but we don't really have any other additional information. So in a sense, it is blind. So here is a here is the one of the time complexity and space complexity that is discussed in the lecture, right? In the lecture slide, and I want to focus on what it means, right? So is it complete? I think you can understand the complete and optimal. Complete means there is a solution to the problem. Optimal is it is like the best solution. So if you go with depth first search, if one branch is infinitely deep, then you will just going down that rabbit hole without coming back up to explore what the best option. So now I want you to focus on the idea of like time complexity and space complexity. The idea of time complexity is that how long will it take to explore a very large tree? So this this data structure is called a tree. So how big, how long does it take to explore all of this and to implement the breadth first search, right? So we define two variables. B is the branching factor, meaning that from one node, how many branch does it branch out? So in this case, it's a 2 branch. And D and M are just like the maximum depth and probably the depth where the goal is, right? So why is time complexity equals 1 plus B squared? Is because if you visit one node, then that counts as 1. So in layer number 2, because it branch out B times, then it takes B times to explore these. At branch number 2, then it is B squared. At layer number 2, it is B squared, right? Because if it keeps branching, every node branch B nodes, then you get this infinite sum. And for this idea, so the idea is that as the tree gets deeper and deeper, the time complexity will approach B to the power of D. D is the depth, B is the branching. That is one way to visualize. And when we analyze the time complexity and space complexity, we are focusing on the worst case, right? So let's say if we are to do the search throughout this tree from left to right, then the worst case scenario is our goal is at the very last, right? So we have to go all the way here, check. Yeah, so it sum out to this B over D. That is also the same idea of the depth first search. So the idea is if you want to reach the worst case scenario, you have to go through them all. So B over M, B to the power of M. So M and D here are like the maximum depth. So same idea. So now is the space complexity. So what does space complexity mean? So space complexity means the memory. In order to go through this tree, how much memory do you need, right? So in this tree, so the node that I colored are the node that is stored in the memory. So why don't we color all the upper branch? Because we have seen them all, right? If we reach this node, then we want to start the next 2 nodes. But after we look through the next 2 nodes, then we can like discard them. So at depth D, at depth D, there are B to the power of D things to remember. This upper part here discard because we have been through them all. What we have not tried is the B to the power of D node that being stored in the memory. So now the difficult one is the depth first search, right? The depth first search. So why is a depth first search B times M and not B to the power of M? So if you recall, depth first search means that we go down on one branch before we look to the other. So if we are at this root, we look, okay, there are 2 ways that I can reach. I can go to the left or to the right. So I start left and right in the memory. So I start these 2 in the memory, right? So even though this is, I will not go here first, but I know that I start an address there. I start an address there so that I can reach it later. So it is still in the memory. But I continue to go down this path, right? Then in this path, I hit another 2 nodes. Then I traverse down this path, but I remember the other one. Similarly, I traverse here, but I also remember the other one. So what makes, so what is the math here? So depth is M and the branching factor is B. So it is like, yeah, B times M. All right, so you go down a branch first, but you still need to store the memory of the upper branch so that you can go back up. I think that, yeah, that will explain the breadth and depth first search. So when in doubt, right? So these are the mathematical analysis. So if they ask you about these time and space complexity, you think of this. But usually they will ask you, MCQ question, what is the sequence of traversal? Just follow this, image, this GIF. Yeah, just the sequence of traversal. Okay, now is where it might get tricky a bit. So this search is called uniform cost search, but I think you can just think of it as, cost search. Like I search with a cost in mind. So you don't really care about this uniform. Just ignore the uniform. It doesn't add anything to our analysis. but the idea is it will add in the idea of the cost. So earlier, all of these branches, they are assumed to have one value, same value. But here, different nodes have different value. So the idea of this uniform cost is you depth first search until the depth that you reach is too expensive compared to an equivalent breadth first. So let's go through this sequence. So at the first, you start at node S. Then at node S, you see that, okay, I have A, B, C as three options. So because A has cost number 1, so okay, least cost, I go A first. So at A, I evaluate, I see G, right? G is 11, but B is 5. So I would choose B over 11. Therefore, the next step is to reach B. So B now give me another node that costs 10. So compared other 3 costs, then I will go to G as well because it is still 10. 10 less is smaller than 11, smaller than 15. So here, this kind of search focuses on the cost, right? As you expand the tree, you continue to count the cost. So yeah, you keep track of the path cost to reach a certain node. So what are the ways that the question might trick you, right? Sometimes they give you a weighted graph, which is the graph with all the costs, the path costs there to trick you to use uniform cost. But you need to focus on what the question is asking you. Sometimes they just ask, okay, just use pure breadth first search or depth first search. How do you traverse this graph? So even though they give you the cost, they just want you to do the simple search like this, right? So that is one way it can trick you. Okay, so now DLS is depth limited and IDS is iterative deepening. This has the same idea of depth first search. Basically, they are just limiting the depth where you can go. So if you recall, depth first search is not complete because if you reach an infinitely deep branch, you will not go back up. So the idea of depth limited is, okay, I limited a certain depth. You cannot go down depth. Yes, you cannot go down it further. Therefore, there is this condition. It is not complete. It is only complete if the limited depth is larger than the goal depth. Because if you limit, so let's say if the depth limit is 1 and your goal is like at level at layer 4 or 5, right? Because you limit there, you will not reach layer 4 or 5. So that is the idea of depth limited. And because of that, right, because it is limited and you cannot reach the lower layer, so they add on the iterative deepening, meaning that at some point in time, you limit at layer 0. After you finish that, you continue to expand layer number 1. Search. Okay. So now I expand the depth into layer 3. Search. Yeah. So you keep expanding the layer. So in this case, because of it keep expanding, right, then it will reach the maximum depth or the goal depth, right? So initially it might not reach down there, but as you iterate, ID is iteratively deepening the limit, it will surpass the goal. So that is the idea. And you can see that the space complexity is B times M, B times L, B times D, because it is the core algorithm is still depth first search. It is just that the depth is limited. So yeah, so you can just remember that BM, BL, BD. Yeah. So that is the idea. Okay, and then why is uniform cost like B to the power of D, right? Then I think I would think that because we don't really know how the weighted graph can turn out. So this B to the power of D is like the worst case scenario, because the uniform cost is like a mix between depth and breadth, right? So the worst case scenario is breadth first search. So that's why it's B to the power of D. Yes. So these are all copy and paste from your slide because I think these are the summary. But now I just want to expand the idea where these number comes about. So this is search. So now we go to informed search. just now was uninformed. Uninformed was quite, it sounds very similar to uniform. So I use blind, right? Blind because I don't know any information. Now I have some information, informed search. So the idea is now I have another matrix which measure the distance or the farness from where I am to where I want to be, from the source to the goal. And I also need to keep track a desirability, the score, a utility of each node that I go through. So just now, if you remember, uniform cost search, I continuously like keep the path cost, right? I keep in mind the path cost of all the nodes and select the one that has the least cost. So when I am informed, I have another heuristics. And if I only use that heuristics, then that is called greedy search. If it is A star, then the cost is the total of heuristic plus the path. Yeah, so these are the three different ideas. Path cost only, heuristic plus path. And I think, yeah, the example that the slide gave is quite informative, really. So initially you have the graph with the different lines having certain values. But these values are the weights, right? The path costs. So what is the other heuristic that we can have when we are traversing between different cities? Is the straight line distance, the straight line, the airplane distance. So even though we are still working on the graph, right? We still need, so let's say these graphs are the ground road. So the road can twist and turn and it's not straight like an airplane flight. But the airplane flight path can give us some, suggestion of how close or how far it is from the two cities. So we use that as a heuristic. Heuristic just mean, a best guess, right? I based on some information to give me a best guess. Yeah. So the idea is if we don't use the distance at all, we use uniform cost search, right? We use, uniform cost. So we only consider the path cost. If we use greedy search, then we will look at the distance only. So let's expand. So from Arad, we want to go from Arad to Bucharest. So Arad's path cost to Sibiu is 140. Zenrit is 75 and Timisoara is 118. So if we only focus on the path, then the smallest path is definitely 75, right? Zenrit. If we only focus on the heuristics, which is the distance, then the distance from Arad to Sibiu is like 253. So we go Sibiu. But when we do A star, we plus them together. And the smallest one is, Sibiu. 100 plus 200 is like 400. Yeah. So it's just, you just block out the value, right? If you want path only, you block out one. If you want heuristic only, you block out the other one. If you want both, then you take both. So that is just the idea. So if they ask you these questions, you just write down, the sequence, the path cost or the heuristics, and make sure that you understand what the question is, right? Sometimes they just want the path. Sometimes they want the heuristics. You can be tricked into using A star because A star is like currently the best algorithm. Yeah, but in the question, you don't use the best. You use what the question asks of you. All right, so this is another green slide, which is because all this graph traversal is under data structure and algorithm, and I think as EEE or CS student, we will definitely learn all these learn all these in your respective data structure and algorithm. And maybe the idea is, okay, should I run through maybe a quick one? So the idea of the first in first out queue and last in last out stack is just the way you do the depth first search or cost or breadth first search, right? So if you do depth, so you go 1, then 2, and you hit 2, you drop down 2. Then when you hit 4, you drop 4 down. Then when you visit 4 already, you put it away. No, this is a stack. Depth is a stack. Sorry. Yeah, depth is a stack. So there is no way to remove 1, right? Because 2 and 4 is on top. So you have to remove 4. Now you go back to 2. So at 2, you see that, oh, there's another 5. So you add 5. Yeah, so basically you traverse one branch before you traverse everything else. Yeah. But for breadth, is you okay, you get 1. Yeah, at the top, you get 1 down. Then from 1, you know that, okay, there are 2 and 3. Then when you are done with 1, you remove the 1 down here. It's like a cube, right? So now you have 2 and 3 left over. And then you keep expanding 4, 5, 6, 7. You stack them up. And then you remove them like a cube, right? First in, first out. Yeah, that's just a visualization. Not important, not question, not tested. Let's move on. Okay. Everyone okay so far? Any question on the search, on the agent, on the environment? Online, do you have any question? I think we're on time. We're on time. Don't worry. Don't worry. Okay, so if no one has question, then let's let's go straight to constraint satisfaction, right? So constraint satisfaction is another type of solving the problem, right? So just now I said there is an agent in an environment and there is a problem to solve. And the problem to solve in this situation is to find the constraint. Some problem like you need to, let's say this problem is the putting the queen on the chessboard so that they won't eat each other. And down here is the idea of coloring. You only have 3 colors. You have to color all the states so that no adjacent state have the same color. So the idea is a constraint. You have to satisfy all the constraints. So one way everyone think about is, okay, what are the possibilities, right? List out all the possibilities, then we will check it one by one. Sometimes people call it like brute force, right? Brute force search. But that brute forcing search is not very efficient. We want things to be efficient. Therefore, we introduce this idea of backtracking, right? So after we put down one queen first, then we evaluate all the possibilities of the second queen. Then if it is wrong, then we go back up to the first one. So let's see. So the first queen goes here, the second queen go next to it. So that's bad. So we go back to this one, check. Not good, go back. Oh, okay, this is good. But what are the next possibilities? So that is the idea. So you can see that the behavior is like depth first search, right? You traverse one branch and make sure that all possibility of this branch is evaluated before you go and check out another branch. So there is an idea of a depth first search. But after you search, every time you enter a node, right? Every time you enter a node, you check with the constraint to know whether you need to go back up or not, right? Okay, so what is the depth first search, right? So what is the termination condition of depth first search? So you go down one branch, and if it is not a goal, you go back up. You go back up. So over here, the condition is you get the goal, right? You reach the circle with the red outline. But over here, it is not about reaching any goal. Like, okay, the goal is to satisfy all conditions. But every time you doesn't meet the condition, you know that it is bad. You go up, you go back up. So yeah, depth first search with constraint checking. Yes. So the second idea of forward checking and constraint propagation is the idea that because you have put down a certain value, and there is a certain constraint that needs to be met, you block out all those constraints as well. Let's use this coloring of diagram, for example, right? So let's say I try to color this state WA as red. So if I color red, I will propagate. If I color WA as red, and the constraint is that 2 adjacent states cannot have the same color. So I propagate that idea towards the adjacent state. So NT and SA cannot have red anymore. So the red is, missing in this piece, right? So let's say I randomly put NT as green, then similarly, SA will no longer have green, and the Q will also no longer have green. And if I colored Q and if I choose to color Q next, then SA cannot be colored by any color, right? Because it is adjacent to all these three color. So there's no color left for SA. So it is an inconsistent, the constraint is violated. So we have to, again, backtrack, so we don't do this fourth square anymore. We go back to the third square and find a different coloring. We need to select another assignment. So you get that idea, right? The idea is that if we hit a constraint, we have to backtrack and choose another possibility. So is there a way for us to, so over here, right? You can choose to color state Q or state SA. So which one do you choose first, right? Here, the fourth square color Q first. But what if we color SA first? And what is the basis of coloring this SA state? So that brings us to two ideas. So what variable to choose, right? What variable to choose? Which values to try first? So over here, back in this chest again. So it seems like you just, brute force search everything. But a more useful way is to pick a strategic variable. I'm sorry. I am very sorry. Yes, so a more strategic way is to pick a variable and choose a value. So I need to separate and distinguish between the idea of a variable and a value. So what is a variable in this problem? So this problem, a variable is a state, right? So this is not this state is like the land state, right? Like this is Australia, the state Australia, province state of Australia, right? So in this case, the variable is the district or the state that we want to color. The values are the three possible options, right? Green, red, or blue. So the idea of a most constrained variable is, so SA here is as adjacent with a lot of other variables. So this is the most constrained, right? So we would try to pick the color for this one first because it is the most constrained, right? And on the right one is the idea of picking the least constrained variable. So in this case, we want to color Q, right? What values do we want to color Q? If we color Q as red, then NT and SA will have two possibility of green and blue, right? So it is more. So there are 2 plus 2 plus 2. So we block. We don't care about. Let's say we don't care about. Let's say we don't care about this bottom 3. Okay, we care about this 4. This cluster of 4. So if we choose Q to be red, then there are 1, 2, 3, 4, 5, 6 values left to be assigned. But if we choose Q to be blue, then there are only green, green, blue, red. So there are only 4 consistent values, right? So over here, we want to be as free as possible, as free to choose as possible. So therefore, we choose to color Q as red so that there are 6 values to choose from, right? I think it is quite intuitive because we deal with constraint satisfaction in our daily life as well. So let's say if we want to arrange a meeting, right? If we want to arrange a meeting and one person is very busy and he's only free on Saturday. So that variable is the most constrained. So we will say, okay, so because that person is not free, we let him decide first, right? So you pick the most constrained variable. And on the idea of least constrained value, we just want more options, right? So if people agree to meet on either a Monday or a Sunday, so of course on a Monday not everyone is free, but on a Sunday a lot of people are free. So that's why we would choose Sunday. because then a lot of people will be free and we will be free to choose, what time do we meet up. Yeah, I think that is a better example than this coloring actually. Yeah, you want to organize a meeting, you let the busiest person to decide first, and you choose the day where everyone is free. Yeah, so again, I think in the question, right, in the quiz, they will ask you this very visual question. They give you a problem, they give you an illustration, and then you just rationalize it out. There is no computation at all. And if you want computation, then this is where how real life people do. So there is this idea of a factor graph. And yeah, so you evaluate all these variables. So there is a variables and then there's a constraint. Again, this is green. This is not tested. I'm just introducing to, excite you, I believe. Yes. Yeah, that is all for constraint satisfaction. Okay, so now minimax. I am told that minimax is very, wait. Yeah, I'm told that minimax is very important and it's very relevant. Then there's a lot of question on this. So the idea of the minimax game playing is now, is not the agent and the environment anymore. There is an opponent, right? There is an opponent that we need to compete against. But the same idea still holds. In order to solve this competition problem, we also need to set up a utility and a score, like a utility or a score to keep track of if the game is favorable or not, right? So in this case, because there's another agent, we want to maximize the score, right? We want to maximize our score and they want to minimize our score. So in this illustration, let's think of the value is a score that is in favor of white. So if the value is very high, then the white is winning, right? White is winning. So this is where we do the min-max tree, so-called min-max tree. So why can we do this min-max tree? If you have studied, let's say, economics, right? There is this assumption that, every agent is rational, right? They will choose the investment strategy that is the most rational. So in this sense, min and max tree is like we are thinking for the opponent. We assume that they are doing the best strategy to minimize our score, right? Min and max are like, yeah. So maybe the opponent is very stupid, right? They don't do the thing that benefit them, but we would assume that they will. So even though the agent is only have its information, it can draw out this minimax tree. So this minimax tree stays within our agent, our white agent, right? We don't know what the black person is doing, what the black opponent, the black chess piece opponent is doing. We don't know, but we would assume that they would do the best possible play to minimize our score. And different from the tree traversal that we said just now. So just now the tree traversal is usually going from the top, right? From the root all the way to the back. In this case, it is usually the case that it is propagating from the bottom node up. So the idea is on the top is the first state. So after white go, then black will go, then white will go. So as we go down the tree, the different people have played different turns, right? And what do I mean by propagate the values up? Is because let's say as we play out the various possibility, there are various terminal state, right? So let's say the bottom nodes are the end point, like the end game, right? These are the end games. And we want to reach this end game. How would we do that? What action do we use? So in the case, so let's focus on this number 3, right? So if we are here and we have the option to choose whether to go to play a move that give us -1 or 3. And because we are white, we want to maximize our score, right? We would play 3. So the value 3 is propagate back up. Similar in this case, we want to play the move that will give us 5. So 5 propagate up. And because we're assuming black is trying to minimize this, we can rationalize that, okay, if comparing between 3 and 5, probably the person will choose 3, right? Will go on this left branch instead of the right. Because if they go on the right, it's in our favor. Good for us, bad for them. But we assume they are smart. So they are minimizing our score. So you can see that, okay, over here, there is a state that is 9, which is the best state that white, the white chess piece can be, right? But why is it that? So in order to reach 9, white has to go to the right branch. But why don't white choose to go to the right branch, but we choose to go to the left? Because if we choose to go to the right branch, even though there is a very high possibility that we will get 9 score, there is another possibility that we get -4. And assuming that the opponent is smart, they will capitalize on the -4. So even though we want to reach 9, they will not let us reach 9. They will choose -4 for us. All right, so this is the idea of propagating the value up the tree instead of traversing down. So at the bottom are the value of the various endgame. Even though we want to reach endgame at value 9, when we propagate the value back up, it doesn't make sense because somewhere along the way, the opponent will cut off our path to number 9, right? So what is the challenge here? So all these 3 branches, deliberation is being computed every time the agent makes a decision, right? So let's say it's my turn. Let's say it's the white chess piece turn. So the white chess piece have to construct this tree, try out all the possibility, and then compute and propagate all the values back up minimax tree, and that is only for one action. After white plays the action, then for the next step, the white has to do the same thing over and over again, evaluating all possibility of the chessboard to construct this tree, right? So that is a challenge because we don't have enough computing power to evaluate all the game. It is not feasible. Yeah, so what are the ways that we can, let's say, try to minimize this tree, minimax tree structure? Is the idea of, so there is this idea of pruning. So we don't have to evaluate all possibility because we can use pruning, this idea of pruning. Or similar to the search algorithm, we can cut off, right? We can cut off searching at some stage. So instead of evaluating all the way from the end game to where we are now, we only evaluate the mid game, right? Okay, mid game score is probably a good estimation of my end game score. So I only look like 100 steps ahead instead of like 1,000 steps ahead. So first, that cuts down the computation. And this idea of pruning, right? Because we know the structure of our tree, we know that if we have 2 nodes and it is under black, then black will choose minimum. So what does that mean over here? So because black is choosing minimum, this value is number 1. We know that whatever value is over here have to be smaller than 1. So we can just propagate an inequality up there, smaller than 1. On the other branch, 5 and 2, it will minimize and get us 2. And because 1 is smaller than 1 and the other is 2, we are 1 to maximize, we will choose 2. Similarly, whatever black choose have to be smaller or equal to 2. But compared to a different branch, this branch is 3. So instead of evaluating everything, we know that, okay, this node is smaller than 2 and this node is 3. Definitely we will go to the left. No time, we don't need to bother evaluating the right. So there are various strategies to cut down evaluating the trees because we know that it is just a mini-max, right? This node will try to min, this node will try to max. Yes. So how would it be quizzes? I believe, yeah, I believe that they will give you the graph and you will just need to make sure that, okay, which node is minimizing and which node is maximizing. And it is alternating between maximize, maximize, minimize. Yes, there will not be any, let's say, you don't have to come up with the tree on your own, I would assume. Usually they would give you the tree. And I believe that if you understand how the minimax tree works and how this pruning works, then you can probably answer the question, right? Yeah, so let's just emphasize why can we prune? Because of the min and max structure, we know that if we have one node is 2, that is 2, and the other node is empty, this node is trying to take the minimum. So we know that it is smaller than 2, smaller or equal to 2, right? And if we compare that with an adjacent node, then we can already make a decision. We don't have to evaluate the different branch. So that is the idea of pruning. Prune like a prune tree, like a gardener, right? A gardener, you prune, you cut down the branches. Yeah, pruning the tree. All right. Now is the last one, like the dreaded reinforcement learning. I believe that this is the hard part. This is the most confusing part. Last time I encountered as well. And I would try to, focus on the main idea. Again, I want you to get A. And learning is extra if you are interested. But let's focus on the A's. Okay. So in reinforcement learning, you see this diagram a lot. So formulation, there's an agent, there's an environment. As you perform an action, you will continue to change the state from ST to ST plus 1. So time step T, you go to state at time step T plus 1. And there is another thing that is called a reward signal, right? You are given a reward based on your action and the state that you're in. So this is the idea. There is the idea of a reward. Is this reward similar to the cost when you're traversing the tree? Probably not. Probably not. Or depends on the problem. Okay, because if your problem can be formulated in, like, let's say a tree style, then it is quite okay, ignore that. It's a different problem altogether, right? So remember that environment has a cost. Hi Bohan, can yeah, don't draw on the slide, thank you. So yeah, so environment will give you a reward for your action. So the objective, right? The objective is to maximize the reward received from start to the end goal. From the start to the end goal. So let's look at the big picture first. Right? Let's look at the big picture. So what is the start and the end goal? So when we go from the start to the end goal, we can call it a one run or one trajectory in the environment, right? Try and error. I do one run, I do two run, I do three runs. So when I finish a run, I have go from the start to the end goal. So what does this big picture mean, right? The idea is that when your agent interact with the environment, it doesn't interact one time and finish. No, the idea is we want to improve the agent by letting it go through the environment multiple trajectories, right? So this is, let's call this a maze, right? As it navigates this maze, it will ultimately, let's say, end up at the goal, which is one, which have the reward 1, or it fall down to a pit, which is a reward -1. So after it reach either of these state, the run terminates. So that is finished the run. But that doesn't mean that the environment and the agent is destroyed. No, the environment reset, but the agent carried forward and continues to try out multiple times in that environment. So this is the idea of going from the start to the end goal. When you go from the start to the end goal, you finish a run. And the agent are allowed to do that multiple times until it knows the environment that it operates in, right? So now let's go back to the Markov decision process. Ooh, Markov decision process. It is very confusing because there are many ways to visualize this thing. So on this slide, there are 3 ways to visualize already. So first is the idea of there is a one state. You take an action, you get a reward, you go to another state. Take another action, you get the reward, you go to another state, right? But this is quite simple, right? When you look at this, you think, okay, this is like very linear. There are not a lot of state for you to look at. But if you go to diagram number 2, okay, this shows, okay, the first diagram shows you the behavior in time, right? ST plus 1, ST plus 2. So different state evolve in time. Diagram number 2 down here shows you the picture of the state and action in space. In space as in S0, S1, and S2 are, on the left, on the right, on the bottom of each other. So this diagram is in space. This diagram here is in time. And what does that mean? So from S0, you can either take A1 to S2 or A0 to S2, right? So this is in space, So from S0, there are 2 options that will lead you to S2. So what does this right diagram mean, right? So this right diagram is a specific environment, right? This is a specific environment. In this case, it is a maze for you to solve. Over here, we are still using a graph, right? Graph-based understanding. So an arrow and circle is like a graph. But on the right is like a problem-specific visualization. So what does that mean? So we can tell the bottom square to be S0, right? S0, S1, S2, S3, S4, S5. So the right from this diagram and this diagram are states and action in space, right? In space. Up here is state and action in time. Down here, yeah. So this big picture gives you the both flavors, right? It gives you the idea that, okay, we go around in space, but as we go one trajectory, it will evolve in time. That might be a bit confusing, but let's stick to the script, okay? Let's stick to the. So what are the main components? So there is a state, there is an action, there is a transition model. What is a transition model? You can see the P, right? P stands for probability. And if you notice, there's also a vertical bar. So if you learn your probability, you have heard of the idea of conditional probability. Conditional probability. What does it mean? What is the probability of reaching state S prime given that I am at state S and I choose to take action A? Right? This is a probability of getting into S prime from S if I take action A. I will elaborate later on. There will be visualization. And of course, there's a reward function. And the solution to the problem is a policy policy pi. Again, go all the way back to the first part. Policy characterize a behavior, characterizes an agent, right? Different agents will have different policy. The best agent will have the best policy. The best policy where the best policy to solve the current environment that the agent is in. Okay? Yep, that is a mouthful, but let's move on. So this is the core idea. I know that the reinforcement learning is quite hard, but if you take anything away from this reinforcement learning part, I hope you take away this expected utility idea. So it is your statistic and probability again. It is just the idea of calculating the mean, the expected value, and in this case, we are calculating the expected utility. So to recall, on the right is, if you are given this value 0, 1, 2, and the probability distribution, and I ask you what is the expected value, you can probably calculate that, which is good. So now let's put that into our current problem. So let's say, so here the square is an action. Around the square is a state. What does it mean? What does this diagram on the left mean? It means that I want to take action A1, but life doesn't get me to S1. 20% of the time I will reach S1 with my action A1. 80% of the time I will reach state S2 with my action A1. Again, why the distribution? It is non-deterministic. It is probabilistic of the action and state transition. So that is why this P, right? Probability. That is why this P comes in. It is a probability. You take action A1, but it doesn't guarantee that you will reach the state that you want. Everything is a probability. So in S1, the utility is 20. S2, the utility is 10. So now the question that they might ask is, so then what is the expected utility of taking action A1? Then you just do your probability E to EX, then you sum up. So 20 times 0.2 is 4. 0.8 times 10 is 8. So 8 times 4 is 12. So even though when I take action A1, I don't know where I end up. I don't know if I end up in S1 or S2. I know that the expected value when I take action A1 is 12. Yes, again, the critical hit again. It is non-deterministic. Okay, more calculation. So now this is where the questions start getting complicated and you might getting dizzy, right? So now you're at S1. There are two actions, right? Two directions for you to go. Action A1 have 20% chance. Action A2 have 80% chance. So yeah, probabilistic action. And then A1 and A2 will lead you to S2, S3, S4, S5. Each of them has their own probability, has their own utility. Then the question might ask, what is the expected value of state S1? Then you do the same thing again. Like first you look at A1, what is my expected value for action A1? 12 plus 18 is 30. Action A2 will be 20 plus 30 is 50. Yep. And then because 20% of the time it will resolve in action A1, 80% of the time is A2, then yeah, you do 0.2 times 30, 0.8 times 50, 46. So when I'm in S1, I have the expected utility of 46 because if I choose to take any action, I will, be at S2, S3, S4, S5. Yeah. So different states have different utility. And if they have this structure of taking action, you can calculate them. Or yeah, you can calculate them. So a different question, same structure, different question. So now instead of a probability, so from state S1, instead of having sometimes A1, sometimes A2, they ask you straight away, I want you to choose a deterministic policy. I want you to choose A1 or A2. What do you choose? Then it is even easier, right? It's just a subset of the calculation that we did earlier. So A1 is what? A1 is 30, A2 is 50. Then now I can say, okay, because A2 gives me more expected utility, I will choose A2. Yep. So more calculation. So I hope I think this is the biggest idea of the whole thing. Yeah. Again, if you take away anything from this, it is just the calculation of expected value. And the way to interpret as well, like interpret why is it that from S1 I have two options? Because I have two options. I can either make it deterministic or sometimes here, sometimes there. And when I take action A1, yeah, sometimes I get critical hit, sometimes I don't. That is the nature of life. Okay, state sequence utility, discounted utility. I was told that it will be involved, right? It can come out, but I don't know the format of the question. So I want to share with you the idea that why is this idea of discounted utility? So if I'm to say to you, I will give you $100 right now, or you can choose to take $100 1 year in the future. what do you take? Of course, you will take it now, right? Because whatever you do in the future has an uncertainty. I promise you $100 now in 1 year, but I'm graduating. So probably you will never see me again. So you rather take the money now, right? So future reward is discounted. And how do we discount that? We add this gamma. So gamma is a discounted factor between 0 and 1. So the idea is that the farther away you are in the future, the more gamma term you multiply. You can see gamma t, right? The more gamma term you multiply, and the value in the future is even less, right? Even though the monetary value is the same, because it is in the future, it has less value, right? So this is the idea. So what is it trying to do? So there is a U and there is an R, right? So what we have been talking about is the utility. So the utility is denoted by this letter U. And then there is the reward. So how do we connect the reward and the utility? So the idea, right? Okay, on to the point of this discounted utility. Let's make another example, right? So the utility score, let's remove this, the utility, discounted utility, right? The discounted utility encapsulate the desirability towards a certain goal, right? So just now I said that there is a start state and there's a goal state, and you want to progress towards the goal. But as an agent, you can only observe what is nearby, right? If you're in S1, you can only go to S2 or S3. You don't really know what is the trajectory in the middle. You don't know where you are going to go towards the goal. You can only see S2 or S2 or S3. So how does it determine which state to go? An analogy is, okay, now I get into uni. Do I choose CS or triple E or like ADM? I don't know. If my goal is to get money, there are multiple ways to get there, right? I can be in FANG, I can be in like chip making. I don't know. I don't really know. But I need to make a decision right now. I need to go to CS or triple E or different majors. So what is, let's say, what is the score, or what is the basis of my decision making at the moment? Probably we can choose, let's say, check the average salary of the major, right? So this idea of the average salary for your immediate action taking is the idea of a utility. So this utility encapsulate the desirability towards this goal. You don't know how it will turn out, but generally it will get you there, right? So that is the idea of this discounted return, right? So why this idea of discounted return? So discounted return is the sum of the discounted reward. The utility is the sum of discounted reward. So if, let's say, we go back up into our this matrix, maze, right? So if our goal has a reward, so this number here, it means that in these black boxes, I don't have any reward. But at the end of the day, I will get a very big reward, 1. So the question is, okay, so if going along this path doesn't give me any reward, right? Then how do I know if I'm closer to the reward or not? So we want to, let's say, propagate this reward back down the path, right? So let's say analogy, right? You want to get money, but you are born as a baby. How do you know that you get money in the future? Then people will say, okay, you want to get money, you want to get a job, you get a degree, you get finish A-level, O-level, finish primary school, secondary school. So the idea of propagating a utility backwards, there are like checkpoints, right? You want to propagate it back. So this is the idea of the Bellman equation, right? This is the idea of the Bellman equation. So S prime, focus on this S prime. S prime is a state in the future. S is the state where I am at now. My point is to propagate that reward in the future, in the future back to where I am. So how do I do that? So first, of course, my current state, do I have any reward? Do I have any reward for being in EEE on my way to getting money? Probably yes. So I add a reward. But then I also add a discounted, it's in the future, discounted factor. And definitely I would take the action that get the maximum value. And this idea of the expected value comes in again, right? The action transition probability. Yeah, action transition. So yeah, after I go EEE, I don't know what is the probability. Like I might end up in a semicon, or I may end up in an automotive company. I don't know. But I will take the action that give me the highest salary. Yeah. So this is the idea, right? Break down term by term. So yeah, so what do you do to get you an A? Maybe you understand, memorize this formula, and yeah, understand how it breaks down, right? It is discounted because it's in the future. You want to take the maximum value, and this is the expected value that you have been calculating. The point is to propagate the utility score from the goal to where you are at the moment. So why take the maximum of expected value? Yeah, probabilistic state transition. We take maximum because we want to reach the goal. And the same thing again. Yeah. So over here we have S2 with probability of 1, 2, 0, right? Then we want to, and we are at S1. Then do we take action 1 or action A2? Then this is the question that we just asked ourselves just now. So if we take A1, we'll get 30 points. If we get A2, we'll get 50 points. So now 30 and 50, we will take 50 because it is the maximum. It is larger. So now 50 will go here. So instead of the max, this thing, we just calculated that. So we replace this whole max as 50. Is there an annotation? Let's do annotation. Okay. So if we go with the, if I annotate, I cannot change slide. Okay. Let's go back. Let's we still have time. No problem. So yeah, let's get back to this question. What action do I choose? How do I propagate the utility score of these things back to S1, right? So here, after we calculate, we know that we want to take action A2 because action A2 gives us a utility of 50. Then here we replace this whole thing. So take maximum action and the utility value give us 50, right? So the question might give you, okay, then the gamma, I give you gamma 0.9 and reward is 1. So what is the utility right now? So 45 plus 1 is 46. Yeah, so this is how you interpret and understand how to apply this Bellman equation. So Bellman equation wants to propagate the utility from future state back to you. And when I said future, right, in this context, the example that I give, right, the going to uni and stuff is in the future. But in our case, right, that's why I need to separate out the idea of big picture in space and big picture in time. In our case, we're not really propagating in the past or in the future, but we're propagating in space, right? Because we're here, we're at the bottom left. Our goal is at the top right, right? We need a pathway to reach the goal. So we want to propagate this reward back to the back in space, not in time, back in space. Of course, you can see that value after 1 iteration and value after 5 iteration. That is because if we keep doing this over and over, right? If we keep applying the Bellman equation for this square, taking the value from the adjacent square, it will give us a different value every time. So the idea is we want to apply the Bellman equation multiple times, 100 times, possibly like thousands of times, so that the reward propagate back in space, right? We run the Bellman equation multiple times in the time domain so that the utility of the state propagate back in time, back in space, all the way to where we are from the bottom left. Yeah. So value iteration. So even though value iteration is mentioned in your lecture slide, I don't really know how it will come out because it is not MCQ or short answerable. But I hope you can understand, right? Propagate back in space. So the idea of value iteration is, right, after we run all the Bellman, then now we need to take action. How do we take action? We just take the greedy action, right? We know all this utility. So if I'm 0, I need to go, do I go up or go left? Go up or go right? Going up give me 0.25. So I will go up and I go up and go right because I'm just greedy. I'm greedy, right? I want the money. I want CS or like big FANG tech company. I just go for the money, right? I don't care. So value iteration, after I propagate the value, I greedy and follow the path with highest value. So what about policy iteration? All right. So again, policy iteration is you are improving the agent. Different agent has different policy. The better the policy, the better the agent. So how do you evaluate the policy, right? So let's go all the way back to our objective. We want to maximize the reward received. So the way we evaluate the policy is to just, count the reward, right? Let's say I can live like 10 lives, right? Okay, first life I choose to be a CS, okay, 1 million. Next life I choose to be a triple E, oh, 2 million, okay. Probably I should choose a triple E, right, in the next slide because I can keep doing it and doing to improve my policy. So that is the idea of policy iteration. So you start at some random pi is policy again. Pi is policy. You try some policy, you evaluate it, and then after you evaluate, you change your behavior to get more reward. Yeah, so that is the idea, right? You evaluate, you change policy, you evaluate, you change policy, you evaluate, you change policy. So what does this triangle mean? It means that at some point in time, you will converge in an optimal value and an optimal policy. Yeah. So this is idea. So up here, again, what is our calculation? We are propagating the utility back in space and be as greedy as we want. Over here, we pick a random behavior. We see if it works, then we try a different behavior and kind of average out and see what works, right? So here we change our behavior. Value iteration, we're not changing our behavior. Our behavior is still greedy, right? We're still greedy. It's just that we calculate the value, we propagate the utility back to where we are. So yeah, so this is again another green slide, and you might ask, okay, so how does this updating of policy works? Do we just randomly choose a new path or a new direction? Then yeah, how do we update policy? We can make a lookup table, and or it can be a function, a mapping. And nowadays in your slide also mentioned there's the idea of deep neural network. So we can also put that in as well to refine our policy, our agent's behavior. So yeah, alternating between the two following steps, evaluate the policy and improve the policy. And I think, is that it? Yeah, I think that is it. And I want you to QR generation. So yeah, so now it's not ended, right? It's the end of the slide, but now is where you ask question. If you have. And I will also want you to fill in the, yes.
So, is there anyone with any question? Because for AI, right, different people have different explanation style. So if anyone of you has any question, you can try to give another type of explanation if you need. So anything that you think you need some clarification, which method that you think you want some clarification? can type into the chat or people who are.
Yeah.
You have 2 year 4 senior here. So
Yes.
you are here to contribute. I'm not sure people can hear. Any questions? And try to type into the chat.
I think this question. Okay, I think you can see this. How you get into fan? I don't know. I'm sorry. That is an example to get the. Yes. Yes.
Any questions?
Pruning. Yes. So the question is, can I explain the pruning part a bit? Yes.
Okay, okay, my name is Lin. So okay, so in short, right, when I'm still learning this thing. Okay, so basically, right, when you will see a full picture of the graph. So basically, pruning, right, something that you need to know about minimax. I'm not sure people online can hear me. Can hear? Okay. So the idea of pruning, actually, you are looking into the future, which means that theoretically, you should be able to know all the end state. Which means that, example, for a 9x9 checker game, cross zero, you should be able to know what is the end goal already. So the ultimate goal is try to win. You assume other people will also do the same. They want to win, assuming they want to win. Okay, so the idea of pruning is that, okay, if I already know that I will be losing in this route, example, I'm playing chess. If I put my queen, anyone here who don't play chess or don't know what is a chess? Okay, so if you don't know what is chess, okay, I assume you know. Okay, so if I example, I'm in the chess. If I put my king to one side, I will confirm be checkmate. Like the opposite, like the enemy will confirm have a method to checkmate me. Like there's already confirmed a method. Like one move, I will be checkmated. Will you take the move? You will not take the move, right? Then you no need to calculate the continual possibility anymore. There's no point in calculating. Example, if I move, then I'm going to. Okay. So example, okay, Hui, I need you, Hui. Okay, let's play a little game because I like demonstration. So example, if I go one step right in front, I know that I'm going to get slapped by Hui. Am I going to calculate the next step after I go there? Am I going to calculate again? There's no point in calculating, right? I know the right side. I don't need to calculate why I need to go in front if I know I'm going to get slapped. Then I just go to other side. SLAP, not SLEP. Okay, so the idea of pruning is that once you know that there is no point in going down the road, then don't go. So let's go step by step if you want to know more about pruning. Okay, step by step. Okay, so you have all the graph already. I will now, okay, so black is min or max? Black is min or max? If you are the opponent is black, I'm white. Okay, so white, I will try to win. So how I win? I get the higher point. So if you are black, if you are black, which one will you choose? You know, you got 8 or 5. Which one will you choose? You will choose 5. And then I know that if I'm at here, which one will I choose? I have between 5 and -4. I will choose 5 because I know that that's my method of winning. So in most of your exam, right, you will calculate all on the left side first, which means that you try to do, okay, 8, 5, 5. I know you will choose 5. 6 and -4. Okay, -4. Or everything propagate up. There's no way to prune. But here comes the pruning. If I know that this one is 1, still that I know that, okay, the maximum that I can get from here, I don't need to calculate the next step first. I know that, okay, this one is smaller than 1. There's no need to calculate the next step. Why? Because I know that if I am the one at 2, right, there's 2 possibilities. If I go one side, I'll get 2. The another route is that I'll get smaller than 1. So is there any possibility that this thing will get larger than 1? There's no possibility because this person, Jinle, will never choose any step that is larger than 1. Example, if this is 2, this is 3. Let's put an example. Can I use a pen?
Oh my gosh, amazing. Okay, so example, if this is 4, let's say this is 4. Is there any chance that Junle will take this step? There's no chance, right? Because Junle will choose the one that is smaller. So relatively, I know that there is no point in calculating anymore because I know that if I'm here, I know that I will choose the one that is larger. And this step will the maximum value will only give me 1. So there's no point in calculating anymore. Understand? So basically is that okay. Actually, when in year 4, when we study this, it's called alpha beta pruning. So if you want to go more in depth, you can go online and search for alpha beta pruning. But basically, you will calculate the whole level first and then compare. Is there any more step that I need to calculate? If there's no point, then just prune the whole thing. Okay? Okay. I'm going to give you a tips. In exam, right? When you're doing the quiz, right? You don't need to do pruning first. You just do the whole tree. Just do the whole tree. Okay, I'm giving some random tips. So you do the whole tree. You calculate every possibility. And then now you foresee into the future. And then you see, oh, this part, actually there's no point in computing, then prune the whole thing. So which means that you calculate everything first, and then you prune away. This is a human method of doing it. If you don't know what is alpha beta, you can just calculate everything first, and then you compare. Oh, this path will never go in, and just cut. No need to calculate. You assume that you already prune. The teacher will know that you prune, although you know that you manually do it. It's okay. Got it?
Yeah. So I think that the idea is happens in different levels.
Yeah, can. Yeah. So the idea, so just now, right? Why don't we need to evaluate these question marks? Because we can propagate an inequality up. So instead of having a definite number, we propagate an inequality up. And because this inequality is smaller than 2, and so 2 is down here, is a different level. And we already have the 3 as an upper level. So when we propagate an inequality, we're trying to minimize, then we can directly compare. Right. So when you calculate up, it's like, okay, I compare min max this one and propagate up. But for the pruning part, the idea is, you notice it is a pruning or not is whether this crucial number 3 is at a different level than the one that you are evaluating. It's just a hint. Yeah, it's just a hint. Is it? Okay. Okay. So branching factor, right? Branching factor is so in the graph that I draw, it is very nice, right? Every node has two children node. So branching factor is just an average number of nodes that the higher up the node is called the parent. The lower one are the children. So branching factor are how many children do the parents have? One parent. Yeah, one parent. How many children do they usually have? So yeah, that is the branching factor. So the idea is the number of nodes, D layer depth is B to the power of D, because every parent have B children, and B children have B squared children because each of them has a B children as well. Yeah, so branching factor is just the number of children a node can have. And in our case, this is like the best case, the pretty case, where all the trees are very nice and symmetrical. But in real life, all the trees are not symmetrical. So branching factor is average, right? Average number of children a parents can have. Here, it is quite clear cut. It is just the number, true, very straightforward number of children. In real life, is average. Okay. Other question. Yeah. Any question from the audience? Yes. Any question from the audience? So I'm not sure if you are still okay with the reinforcement learning. So I think in terms of, I hope I have give you the, let's say the understanding of reinforcement learning or the decision process, right? So I hope that you can do all your, let's say essay, or not essay, but short answer or MCQ question based on how reasonable it sounds, right? If something is unreasonable, probably it's not true. But let's stress the calculation that you need. First is you need to calculate what is the expected utility, right? Going through the various example that I shared. Secondly is this idea of discounted utility where the gamma gets in, right? So sometimes it's nice as, you know, like just gamma to the power of TR. Testing. Why am I freezing? Can you still hear me? Can still hear, but it's freezing. Okay. Yeah. So the second equation is, yeah, the gamma, how the gamma comes into play. But I also don't suspect a lot of calculation here. The third one is this Bellman equation, the way you propagate the utility, right? Over here, you are calculating like the average, like the expected utility. But the proper way to propagate it back is to use this Bellman equation, right? Because let's go look at the bottom right diagrams, right? It is here. So if we continue our expected value, we can calculate an expected utility of S1 based on S2, S3, S4, S5. But the idea is that is just, it is not a good way to propagate. A good way to propagate is to choose the best action, right? Add a discounted factor and add the current state reward, right? So yeah, I think that this is an important point. What is the difference between the Bellman equation and this idea? So over here, the question is, what is the expected utility of state S1, right? So here you just apply the expected value multiple times. The first round for A1 and A2, then the second round for S1. But this is not the correct way to propagate the value, the utility from S1, S2, S3, S4, S5 to S1. This is not the proper way to propagate. The proper way to propagate is to use the Bellman equation, right? So you evaluate the expected value, but you stop at the action. You stop at A1 and A2. Then you select the best action, either A1 or A2. From there, you multiply with the discounted factor and add the current state reward, right? Just like I have done just now. So instead, so just now we calculate this is 50, right? This is 50. Let's say this is 0.9, reward is 1, then we get expected value to be 46, right? Expected value to be 46. But up here, oh shit, it's 46. Okay, wrong. Yeah, it happens. It turns out to be that way, but it shouldn't be. So if I change the, yeah, let's say if I change the gamma to be 0.8, then you get 41, right? Instead of 46. That is a happy coincidence. But the idea is to calculate the expected utility of S1, you follow the Bellman equation because there is a distinction between the current state and the future state. If you just do this, then there is no distinction between the future and the past, right? You're just averaging out. So it is not a good way. But maybe they can ask like this. What I'm trying to demonstrate here is just the idea that you can calculate the expected value multiple times, multiple times in a row. So those are the three main equations for the reinforcement learning part, right? Bellman, this gamma discounted utility, discounted factor for the discounted utility, and the expected utility. These are the three equations for the reinforcement learning component. Yes. Do we? Okay, you can.
Okay, so
I'm back, guys. Okay, so I think the most straightforward method for alpha beta pruning, sorry to go back again. So we do one question together, alpha beta pruning together. I think that will be easier for you to understand. So everyone put up your paper if you need one. So
You want?
can I have a blank
Okay, can
screen?
you share?
Nah,
You're in
no,
the
no, no.
chat.
It's okay.
Just go down.
Okay, so I will get one. Oh my gosh. So new slides.
Yeah.
Okay, how to present? Oh my gosh, you four don't know how to present. Okay, let's do a very simple question together. So let's say that we have this state, and then okay, I'm copying from the lecture slide. So thank you, Prof, for providing me the answer. Okay, so we have these three. Okay, that's two. By the way, that's two. I know the handwriting sucks, but don't care. It's okay. Okay, this one is 5. This one is 7. Okay, let's do pruning together. Okay, so okay, I haven't write. This one is mean because we are doing what is the code? Mini max. Yeah, mini max. So max mean. Okay, it doesn't matter, but okay, I write mean. Okay, so let's propagate step by step. Okay, first step. Can I change color? Okay. Okay, so if I'm here, can you see my cursor? What will I choose? I will choose 3, right? So which means that the minimum it will be smaller than 3. Okay, can I understand? Means that everything that I can choose, this one is the first step. Okay, first step. So far, so good, everyone. Smaller than 3. Okay, now I know that. Okay, max, like I can only get smaller than 3. Okay, next iteration. Now I look at the left side. Okay, I go to the other side. Okay, so what is the possible value of this? Is 5, right? 5 or 7? Okay, let me 5 or 7. Okay, I will choose. Okay, can I go back? Okay, 7. 7. Okay, but will I okay, this is not a good example. Let me try to let's dump. Yeah,
Erase 7.
yeah, erase 7. Okay, actually it doesn't matter, but okay, I'll just make it simple first. Okay, let's say it's 2. Okay, so what is the max? Okay, because I'm doing that first search, I will look at the left side. Actually, but okay, I will look at the left side. Oh my gosh. I'm taking this exam. If I can get A for this, you can also get A. How confused I am. Okay, second step. So I'm doing that first search, guys. I'm doing that first search. So I will look at 5. So the maximum, I haven't looked at this. I haven't looked at this too. I haven't looked. It's just there. I haven't looked. I'm doing that first search. So the number that I will see is 5. But is there any chance that I will go to this side? There's no more chance because I will choose the minimum. The maximum here is 5 already. So no matter the value here, example is 2. Even if it's 7, this will go 7, but anyway will go down. I will never go down because I'm minimum 3. I already can get 3 on the left side already. Why should I need to evaluate on the right side? So which means that once I know that this one is 5, I immediately know that okay, this I can get 3 already. I can get 3 already. There's no point in looking at another number already. Then I prune away this number. Actually, from the 7 just now, it also apply, which means that if this number is 7, okay, I'm just trying to prove to you why I don't need to check the other number. If this number is 7, remember, I'm doing that first search, which means that the only number that I will look when I'm checking, I will check this thing and check this one first because I'm doing that first search. I won't check the other node first. I will check the node that first search. I will check the left side first. I will get 5. There's no point in checking the another number already because I know that I will choose the minimum and this node maximum already will give me 5 already. Without checking the next one, I can just prune away this one. There's no point in checking anymore. So does that make sense? There's no point in checking the another route if I already know that I will get a better value from one side. There's no point in doing another calculation already. Does that make sense? Does that make sense? Or you want to give bigger tree? I have 3 layers.
Okay.
I have 3 layers here. Okay. Thank you.
Yes. Any other questions? And clear. How do I clear? Yes. So I guess if you have no question, then you might want to fill in the QR code for the feedback. Yes. Oh, we are sharing. Yes, yes. We will be sharing and like clean up the slide and maybe from the input from the question that you have today, then we will add in some more. Then we will share the slide and wait for the recordings to go down as well. Yeah. Iteration. Okay. Pruning. Okay. Thank you very much. From the online participant, do you have any questions? We will still be here until 9 as stated. So if you have questions, do raise them up. There is a request to run through the accessible, deterministic, and sequential part. So accessible is the idea that does your agent knows about the world, knows everything there is about the world. Let's use examples. Let's use example. I have a lot of examples. So first, slot machine, you don't really know what the wheels are, and right, the back wheel is like hidden. So probably not. Chess, yes. Pong, yes. You have the whole board. Space Invader, yes. Everything is up there. Monopoly, no. Right. Monopoly, you don't know what your opponents have. Right. What are the community cards or the chance cards? You only know the partially. Like you only know where you have to go on the board. Walking bot simulation, yeah. They only know how to move their limbs. So it's also partial. StarCraft, yeah, partial. I think the question should be quite straightforward. In terms of what are the parameters, what can you see, what can you really see? So if it is a game, and it is easier because when you're in a game, there is a predefined set of rules, right? So if they ask, is a chess accessible? Yes, definitely. Let's say is self-driving car fully accessible, even though there's a lot of sensor? Probably not. Probably it is still an inaccessible environment. Yeah. So I don't think they will ask trick question like that. It should be straightforward. deterministic and sequential. Deterministic is about the action. So just now, like the calculation that we run through, right? Sometimes you take an action, but the state that you landed on are different. Why is this the case? Because of the nature of the environment itself, right? There are parts that we cannot control. So connecting to the accessible, right? Like we can access, we can see the world, but we cannot really determine how we move in the world, right? In the let's say in the League of Legends example, this one, you can see the enemy moving. It is like accessible knowledge, but when you fire a hit at the opponent, the critical chance you don't know, is it a critical or it's just a normal shot? So deterministic or non-deterministic exemplify that, right? So in a quiz, let's say in a quiz, what are the hints, right? Let's say the Monopoly, like if the game involves rolling the dice, probably not. I think it is highly likely, right? It is non-deterministic because you have to roll the dice, and rolling the dice determine where the state you will land it on. So yeah, that is deterministic. Episodic and sequential. So episode, how do we determine an episode? Episode is one loop of I see the world, I make decision. See the world, think, make decision. So when after I make the decision, is that decision and is that state still relevant for the next decision making, right? For things like chess, Pong, and I'm pretty sure on the from chess and Pong all the way to the right on the screen, they are all sequential, right? You need to know what happens before and then react to what happened before. Slot machine is like episodic. You roll one click and then it rotate, and then it is just like random chance all the time, like in the future. So you cannot really, you cannot carry any knowledge forward in time. And what else? Episodic. Another episodic, let's say environment is, let's say an image classification. We usually not think image classification as an agent interacting with environment, right? But sometimes you can classify it as that. So image classification is like I give you a picture, whether it is a dog or a cat. So I give you a picture of a dog, then you say, oh, it's a dog. I observe, I think, I act, I said it's a dog. So when you give me a new picture, the old picture doesn't have any resemblance to the new one. So it is discarded. It is episodic. I'm done with the decision making last time. I continue to the new decision making, right? Pong, in the case of Pong, right? I move the pad up a bit, but if I move it too much, then okay, I need to slow down or like reverse the course. So I have to consider like my past action and subsequent action as well. So yeah, so those are the accessible, deterministic, and sequential. On that point, right, like different question can be tricky. So discrete or continuous, they should be straightforward. Let's say in a chess, everything is discrete. I don't think they will say, oh, is Monopoly discrete or continuous, or like is StarCraft discrete or continuous? That is too much, right? Too much to be on a quiz. So don't worry. Yeah, so I just shared the various agent and environment. Okay, thank you for coming.